Hello viewers, I am Dr. Thayalan, Chairman, Radiological Physics Foundation. So we have been watching the videos from Thayalan Talks YouTube channel. Last class we discussed about the ionization chamber and GM counter. Today we are going to talk about scintillation detector, which I find very good applications in radiological sciences. Let us pass on to the slides one by one. So let us start with the introduction. We all know that radiation can cause ionization and excitation in matter. Ionization is the removal of electron from neutral atom. Excitation is raising the atom to the higher energy level. After ionization, what happened? The electron can recombine with the atom, or after excitation there may be a de-excitation process, that is excited atom return to the ground state. So during that process they emit thermal energy. This thermal energy has appeared as molecular vibrations in liquids and gases or lattice vibrations in crystals. However, there are some materials which emits visible light and ultraviolet after irradiation. These materials are called scintillators. The detectors made from this material is called scintillation detectors. What are the type of scintillation detectors? It is inorganic scintillator. It is usually made up of solids. Organic scintillators are plastic or dissolved in liquid solutions. In both cases, the emitter light is proportional to the energy deposited by the ionizing radiation, such as alpha, beta, and gamma rays. How much light is emitted from the scintillation? The emitter light is so small. For example, if you take a gamma rays of energy 70 to 500 kilo electron volt, it may emit 100 to 1000 photons per single gamma rays. So initially olden days what they did, they observed and counted the amount of light. Whereas today what we are going to see, we are using photomultiplier tube, that is PMT or PM, or photodiode we are using to collect the light from the scintillator. This photomultiplier is ultra sensitive so that the signal is recorded very efficiently. So which actually scintillate? Atoms and molecule do not scintillate. Only crystal can scintillate. That too, pure crystal cannot do the scintillation because, for example, if you take sodium iodide, it can scintillate only at liquid nitrogen temperature in a pure state. So always what we do is crystals added with impurities. For example, if you take a sodium iodide, it is added with a thallium. Cesium iodide added with thallium. This impurity we call it activator. So these impurities are very mainly responsible for the scintillation of the crystals. Let us see the scintillator principle. When ionizing radiation incidents, what happened? The electrons are raised to the excited state. While they are returning to the lower energy state, visible ultraviolet light is emitted. The photomultiplier tube converts this light into electronic signal, which is proportional to light intensity, or it is in turn it is proportional to the incident radiation energy. The light emission increases with increasing energy deposited. So most of the scintillators are operated in pulse mode as spectrometer. The energy resolution is based on the crystal characteristics. That means each crystal has its own characteristics. So based on the characteristics, the energy resolution of the scintillator behaves. What are the various characteristics of the scintillation crystal? See, for example, conversion efficiency is very important characteristics. The how much light it falls, how much radiation it falls, how much light it produces. So similarly, the decay time. So after the scintillation, what happened? How short, how quick actually the electron comes to the lower state. That is called excited state time. and then it should be transparent for light, and also it should have high Z so that high detection efficiency is there. So it is rugged, unaffected by moisture and inexpensive. Apart from that, you should also having a matching between whom light emitted as well as the spectral sensitivity of the photomultiplier or photodiode. So this table tells you about the radiological scintillator, that is the scintillator material used in radiology. You see in the first column sodium iodide with a thallium and bismuth germanate, cesium iodide, cadmium tungstate, calcium tungstate and gadolinium oxysulfide. So these are the various density of the detectors and atomic number and conversion efficiency and decay constant in microseconds. This is the afterglow. So decay constant means after excitation how quick actually it come to the normal ground state, that is a time in microsecond. Afterglow, once the light is emitted, how far the light is active in the system, that is called afterglow milliseconds. Generally afterglow must be very minimal. Lowest afterglow is the best detector to be used. Probably sodium iodide with thallium is the oldest one and actually had find large application radiology. They use it in gamma camera, they use it in first CT scan, etc. So these are the scintillators used in nuclear medicine in terms of density, effective atomic number, decay time, photon yield per kilo electron volt, refractive index, microscopic, peak emission in nanometer. Various crystals are given: sodium iodide with thallium, PgO, LSO, GSO, CSI, lutetium and LaBr2 and plastic. This is organic scintillators is used. So let us see the sodium iodide with the thallium. Sodium iodide is one of the oldest scintillator crystal used in nuclear medicine in pulse mode. It is used in gamma camera, thyroid probe and gamma well counters. It provides high photoelectric absorption probability. It has a high conversion efficiency so that it provides good energy resolution. It can be made as large crystals, even 59 centimeter long, 44.5 centimeter wide and 0.95 centimeter thick. It is actually fragile and hygroscopic, requires chematic sealing. What is meant by hygroscopic means it absorbs water from the moisture. So that's why actually the crystal or the instrument having this sodium iodide should be kept in a good temperature and humidity maintenance. There are some scintillation crystals are used in a PET detectors. Usually these crystals are very thick, high density and high atomic number. For example, we can talk about bismuth germanate, that is called BGO. Lutetium oxyarthosilicate, it is known as LSO. Lutetium yttrium oxyarthosilicate, known as LYSO. Oxyarthosilicate, known as GSO. The chemical formula is given in the slides. These are the various detectors used in positron emission tomography. Let us see about the photomultiplier tube. What is a photomultiplier tube? It is an electronic tube which is sealed in a glass and it is also evacuated. What is the dimension? 1 to 7.5 centimeter diameter. What it does, photomultiplier tube converts light into electric signal. In addition, it also does amplification. That means it performs both work. The front entrance is coated with the cesium antimony photocathode. So this is a commercial photomultiplier looks like. So this is connected to the light entrance and this is actually the PMT. The conversion efficiency decide the quantum efficiency of the PMT. So how much actually the radiation is converted to light, that's more important. In addition to that, the photocathode how much electron it can produce. Suppose 10 ultraviolet or 10 light photons for incident, it produces 1 to 3 electrons. So the photomultiplier tube also has number of diodes. The diode number may be 10 to 12, and it also has an anode. Each diode there is a increase of voltage in steps of 100. That means if the first diode is having 100, the next diode will have 200 and 300 and so on. There is a focusing grid that directs the electron towards the diode. When the electrons falls on the diode, what happened? It produces 5 secondary electrons per electron. So suppose 1 electron falls on the diode, 5 secondary electrons are produced. Actually, this we call it amplification. Similarly, for each anode, additional electrons are produced, so the electron number goes up. So you can see the picture here. This is the diode. Diode 1, diode 2, diode 3, diode 4. This is the anode. So this is the photocathode. The light comes here. The light falls on the photocathode, produces electron. This electron goes and produces secondary electron. In this you can see one electron produces 3 track. Similarly, what will happen? Each produces 3 tracks so that the final electron number gets amplified towards the anode. So suppose if you take a case of 10 diode of 5 amplification, the total amplification is 10 power 10, that is equal to 100 lakhs. So therefore the number of electron produced here is equal to 1. You will get 100 lakhs electrons here in this point. So this what we call it multiplication factor. So how it depends upon, what are the multiplication factors depends on. The multiplication factor depends on photoelectron energy, voltage difference between the diode and the photocathode. So how to focus the electron? The electron focusing can be done by external magnetic field. So generally the photomultiplier tube is often wrapped in mu metals, foils for magnetic state. What mu metal is? Mu metal is nothing but iron, nickel, copper and chromium. The scintillator PMT needs to be coupled properly, for which they are using optical coupling to minimize reflection losses. And also the scintillator is surrounded by magnesium oxide powder, for which is a reflective material. What are the various applications of the scintillators? Scintillators are oldest detectors. For example, barium platinum was used by Ranjan during the X-ray discovery. So film screen radiography, from olden days we started using calcium tungstate for many years as intensity screen. Nowadays it is replaced, calcium sulfate is replaced with rare earth phosphors, that is gadolinium oxysulfide with impurity terbium. In digital radiography we are using cesium with a thallium impurity. Fluoroscopy we are using input output phosphor. The input phosphor is cesium iodide with sodium impurity. Output phosphor is zinc cadmium sulfide with silver. In CT scan, cadmium tungstate and gadolinium ceramics are used as detectors. Let us see about the photodiode. Photodiode is basically a semiconductor diode, example silicon. It is operated in reverse bias mode. It converts light into electrical signals. The light photon does ionization with the silicon so that charge is released. The total charge is proportional to the intensity of light. This is the basic principle of the photodiode. Photodiode has higher quantum detection efficiency, around 60 to 80%. They are in smaller in size, less expensive. They do not amplify signal as PMT. This is the basic difference. But nowadays what happened? Avalanche photodiode, APD, operated at a higher electric field, is available for with more gain. That means it can amplify the signal if you use APD. Photodiode produce more noise than PMT. It is photodiodes are used in indirect digital radiography, flat panel devices in fluoroscopy. Cadmium tungstate with the photodiodes are used in CT in current mode. Let us talk about the organic scintillators. The organic scintillator basic actually the mechanism is molecular excitation. So during the de-excitation what happened? The scintillator absorbs energy and release visible light. Organic scintillators may be a plastic or liquid scintillators. In the case of liquid scintillators, it has solvent, primary solute, secondary solute and additive. These are the component of the liquid scintillators. Organic scintillators is very good for low energy X-rays, gamma rays and non-penetrating radiations. And also it is very good while we are making assay of radioactivity specimens with the blood and urine. But they are inefficient detectors for penetrating radiation. Organic scintillators suffer from quenching effects. That means the reduction of light output from the sample, which is variable one. The causes for the quenching may be chemical quenching, color quenching, and dilution quenching. Quenching correction methods are available nowadays to overcome the above effect. I hope you enjoyed the video. Kindly subscribe and succeed. We will come back with another video in the next session. Thank you very much.